Picture this. It is 10 degrees below zero, and your survival depends on the pile of wood in front of you. But the match just keeps going out. Panic sets in. Why is this happening? You have wood, you have a match, and you have air. But nature has a strict set of chemical laws, and right now you are breaking them. Welcome to the science of combustion. To understand why your fire is failing, we first have to look at the fundamental architecture of fire itself, known as the fire triangle. Most people know the three legs: oxygen, heat, and fuel. It's often visualized as a large equilateral triangle, with each side representing one of those elements. But here is the catch that most people miss. Having these three things isn't enough. They must interact in the correct ratios and, crucially, in the correct chemical sequence. If you have a log fuel and air oxygen, why doesn't it spontaneously burst into flames? Because you are missing the catalyst of sufficient heat to bridge the gap. Today, we are going to break down the invisible chemistry occurring at the molecular level of that log, and by the end of this, you will never build a bad fire again. Here is the first major conflict. Size matters, but not in the way you think. You might believe a big log equals a big fire, but chemically, a big log is actually a heat sink. It absorbs energy rather than releasing it. This brings us to the concept of surface area to mass ratio. When you hold a match to a giant oak log, the thermal conductivity of the wood dissipates, that heat deep into the core of the log before the surface can get hot enough to react. It's like trying to boil the ocean with a candle. However, if you take that same wood and shave it into thin strips, you increase the surface area exposed to oxygen while decreasing the mass that steals the heat. This allows the heat to stay localized. The heat builds up faster than it can escape. This is why tinder works. But here is the pattern interrupt. You get the tinder lit, you throw on a medium stick, and the fire suddenly dies. Why? Because you suffocated the reaction before the chain reaction could become self-sustaining. You moved up the fuel ladder too quickly. Now let's get into the deep chemistry. Here's a fact that might surprise you. Wood does not burn. I repeat, solid wood does not burn. When you see a log on fire, the solid material isn't what is flaming. It is the gas escaping from the wood. This process is called pyrolysis. Imagine a log being heated, with invisible wavy lines of gas rising from it. When wood reaches about 300 degrees Fahrenheit, it begins to chemically decompose. Long chains of cellulose and lignin, the structural backbone of the tree, start to vibrate and break apart. As they shatter, they release volatile gases: methane, methanol, and hydrogen. It is these gases that mix with oxygen and ignite to create the flame you see. The solid char that remains burns later, but the bright yellow flame, that is burning gas. If your fire won't start, it means your wood isn't hot enough to vomit out these gases yet. You are heating the solid, but you haven't triggered the decomposition phase. You are stuck in the preheating zone, wasting energy. However, there is a silent killer lurking inside your firewood, and it is the #1 reason fires fail: water. Even dry-looking wood can contain 15 to 20% water weight. This leads us to a thermodynamic nightmare called the latent heat of vaporization. Before your wood can reach 300 degrees to start pyrolysis, it first has to reach 212 degrees to boil off the water. Imagine a temperature graph. As you apply heat, the temperature of the wood rises, but then it hits 212 degrees Fahrenheit and flatlines. The temperature cannot rise above boiling until all the water is gone. This is an immense energy cost. It takes roughly 2,260 joules of energy to turn just 1 gram of liquid water into steam. That is energy your match is providing that is not going toward burning the wood. It is effectively being used to dry the wood. You are not building a fire. You are running a kiln. The steam rushing out of the wood pores literally blows the oxygen away from the surface and cools the reaction down. If you hear hissing, that is the sound of your fire dying. You must use dry, seasoned wood to bypass this energy valley. So how do we apply this? We need to talk about activation energy. This is the specific threshold of energy required to kickstart a chemical reaction. For wood gas to ignite, you need to reach approximately 540 degrees Fahrenheit. This is your target. If your kindling burns at 400 degrees, it will never ignite the log next to it that requires 540 degrees. You need a stepping stone approach. Start with paper, which ignites at 451 degrees. Use that to heat twigs, which burn hotter and longer. Use the twigs to heat branches. You are building a thermal ramp, a staircase of temperature. Each step must provide enough excess heat to raise the next piece of fuel to its flash point. If you skip a step, say, going from newsprint to a 3-inch log, the paper burns out before the log reaches 540 degrees. The log falls back down the temperature scale, and you are left with smoke and frustration. Smoke, by the way, is just unburned fuel. It is pyrolysis gas that didn't get hot enough to light. If you see smoke, you have fuel and oxygen, but you are lacking heat. Now, let's address a hidden variable that most people ignore until their house fills with smoke: the physics of airflow. You might have dry wood and a hot match, but if the air isn't moving correctly, the fire dies. Fire breathes. It needs a constant stream of oxygen. As hot air rises, it creates a vacuum at the base of the fire, pulling fresh, oxygen-rich air in. This is the chimney effect or the stack effect. But here is the twist. Cold air is heavy. If your chimney or fire pit is full of a plug of cold air, the hot smoke cannot push it out. The fire chokes on its own exhaust. Before you light the wood, you often need to prime the draft. Light a torch of newspaper and hold it up the chimney to push that cold air plug out and establish the updraft. Without this convective current, the oxygen supply is cut off. The fire triangle collapses because the oxygen leg gets kicked out by the waste gases, the carbon dioxide, settling on the fire. So taking all this chemistry and physics into account, pyrolysis, latent heat, surface area, and airflow. What is the perfect solution? It is a technique that looks wrong but works perfectly. The upside-down fire. Most people build a teepee or put paper on the bottom. This is inefficient because the heat rises away from the fuel. Instead, lay your largest logs flat on the bottom, tightly packed. Then, lay a row of smaller logs perpendicular across them. Then you're kindling. And finally, your tinder on the very top. Why does this work? 1. The heat from the top layer radiates down to preheat the logs below, drying them out before they need to burn. 2. No heavy logs can collapse and crush your airflow. And 3. The smoke from the bottom logs has to pass through the flame on top, which burns the smoke, reducing pollution and increasing heat. This utilizes gravity and thermodynamics in your favor. It creates a long-burning, self-feeding reaction that requires zero maintenance. By stacking your fuel upside down, you ensure that as the top layer turns to charcoal, it falls onto the layer below, providing the exact activation energy needed for the next stage. It is a chain reaction of physics perfectly aligned. So the next time you are out in the cold or just lighting up the fireplace, remember, don't just throw wood in a pile. Think like a chemist. Respect the water content, calculate the surface area, and manage the airflow. Fire isn't magic, it's a recipe. And now you have the formula. If you want to learn more about the thermodynamics of everyday life, make sure to subscribe and follow. We break down the hidden science of the world around you every single week. Stay warm, stay safe, and keep experimenting.